There we go. Hey all. So I don't have to do the same long introduction as Dr. Ali since I taught half of you at least. But just like last week, which dealt with a lot of signal processing in audio, this week we're going to be talking about signal processing in video and to a much lesser extent images, which are just part of which makes up video. A lot of the work which I'm going to be talking about today was the foundation work for my thesis at Trinity College Dublin. I could talk to you all a little bit about that program as well at the end of this, but I want to make sure that we get through the actual content first. So, three things which I want to focus on today. Understanding rate distortion trade-off and how to graphically represent it, how to identify methods of compressing video, and identify potential applications of video compression. Now, here is the general compression scheme. This is true for any signal. This does not need to be limited to video or images or audio. Any signal can be compressed by manipulating the data about it. There's two types of compression, lossy and lossless. Lossy compression has losses, but it allows you to get the gist of the signal regardless, whereas lossless is a way of compressing while mitigating any loss in data. And the way which this is, we have in compression, we have two directions. We have encoding going from our source to a compressed bit stream, and decoding going from a compressed bit stream to some viewable media. Usually that viewable media should be near identical to the source. And there are three steps in between. The energy compaction, where you are taking some form of transform of the signal in order to reduce how many bits or what is needed to transfer that information. Quantization, which is usually in image, audio, and video compression, some form of rounding, because a lot of times you can't represent things to the number of decimal points, which is a true representation. Some symbol compaction, which takes advantage of some repeated information or the statistical probability of information occurring and using that property to compress, and then you have our compressed bit stream. It's important to note that in decoding, there isn't like a dequantization step because once you chop off, you're rounding off, you have no way of knowing what was there before. Uh, Fun way of thinking about it is like when you were doing add math in integration, you had no way of knowing what your plus C was for a lot of these differential and integrate, all lots of these calculus questions. If I say that something was approximated to 2.5, you can't tell me whether it was 2.45, 2.46, 2.47, 2.51. You have no idea of knowing. So there isn't any way of dequantizing. So once you quantize, it's chopped. So why am I talking about video? Video is at least 80% of all internet traffic, including this right now. That our video streaming lectures counts as in that 80% of video of internet traffic. And this was an estimation done by Cisco in 2021. It is quite likely that this number has gone up in terms of the internet traffic because video continues to grow more and more popular and larger with the amount of higher resolutions and higher frame rate video which exists. Think of Twitch is streaming, all the streaming services, whether it's Netflix, Disney Plus, YouTube, Vimeo, the whole works. And no matter what, the demand is for high quality, low bitrate video. Now, high quality seems obvious because we want to see things which don't look like they were shot on a Nokia 1100. And each time I make these references, I forget that y'all were born in 2000 or later. So let's use just on a 144p, any of these low resolutions where you're seeing the pixels. You don't want that. You want something looking crisp, something looking with all the detail. But low bitrate, that is often lost as to why we want this. So this could be done in the chat or if people could unmute. Your cell phone data plans. How many of you have run out of data because they forgot that they were on data and watched Netflix? Has this happened to you, or is everyone responsible? Let's see a thumbs up from Tony. Everyone else has been good, and Kyle. Everyone else has been, and Faz is laughing at me. And everyone else has been good and made sure that they were on Wi-Fi or paid for their unlimited or whatever. The smaller the video, the less likely you are to think. Brandon, is that a hand up for agreeing or a question? It's for agreeing, I think, because it went back down. And that is the main goal of video compression. So we want to high quality, small file size, or small bitrate. Now, video itself is diverse. Here is a sample of videos from YouTube's user-generated content data set that we have a 25 videos on screen or 30 videos on screen, and they all look different. And no two videos do look different, but there are certain properties of videos which we want to pay attention to in compression. And that was what my thesis was about, to tailor codecs to the video content to maximize compression. Today, we're not going that far. We're just going to be talking about what is compression and how it's supposed to look. So here we have a rate distortion curve. On the x-axis, we have our bit rate. It's measured in megabytes per second, and that's a bit that relates to file size. And then up here, we have our peak signal to noise ratio. In ECNG 2001, you all have been familiar with signal to noise ratio, where you're trying to have infinite signal and zero noise. So ideally, would want this to be as high as possible. So what did we say we wanted? We wanted a high quality. So high quality will be more signal and less noise. So we want to be up. And so up top. And we want a low bit rate. So we want to be down low. So our ideal situation is being in this top left corner. What we have here in this rate distortion curve, I've encoded the same video with different properties, and we're going to look at that video in a bit. We have a bit rate of 4 megabytes per second and a PSNR of like 33 point something, a very low bit rate with a low PSNR, and something in between, like Baby Bears Forward. So we're going to look at these videos. So we see A, B, and C. In the chat, which one of these videos is the worst quality? And I know that this is me playing a video through a video streaming on dodgy internet, so like it doesn't always work well. All right. C, correct. Very good. And the next question I have is there enough of a visual difference between A and B that it would bother you? So that is a yes or no question. No, from Ashley and Dana. Right. But the difference between B is half the file size, approximately, than A. So we see that we can take advantage of the fact that there is a loss in signal, but we don't care sometimes. So now we can represent that curve a bit mathematically. And this is the goal of any video compression scheme, or any compression scheme, to be honest, that we have some objective function, which we're calling J, the goal is to minimize J. And we have this trade-off. We have our distortion, which is usually represented by some quality metric. We have our rate, which is represented by R, and we have lambda here, which is a trade-off. We saw just now that there is a link between the distortion, the quality and the rate, and quality is 1 over the distortion, because the opposite of distortion is quality. That if we're trying to minimize A's rate, we're going to end up increasing our distortion. And if we try to minimize our distortion, we end up increasing our rate. So you know that little 3-switch thing of sleep, grades, social life, and you can only have 2 working at any point in time? That's how this ends up working, that getting minimum distortion while getting minimum bit rate is a problem because they are intrinsically linked. So the codecs have this trade-off function, and they're trying to figure out a way to minimize both in such a way that the combination is minimal. So that's what compression is and the goal of it. So how do we compress? So the first step, we could look at each individual frame. A video is a series of images. So when you hear frames per second, it's how many images in a given second. So most standard video is 24 to 30 frames per second. A lot of gaming video is 60 to 120 frames per second. Slow motion video, it tends to be all the way up to 240 frames per second, that we have a single frame over each second. We have multiple frames per second. And we can compress each image using standard image compression tools. One of the more common ones which is used is JPEG. You would see a lot of your images saved as a .jpg or a .jpeg. And this has a few steps in it. We could have it deal with whatever color scheme. Most color images are in red, green, and blue format, but some folks would ask that you convert it to something which has to do with the luminance and the chrominance there, which is like the light intensity and the color intensity. And then for each plate, we end up scanning block hooks that we divvy up the image into a series of 8x8 blocks. The size of these blocks have changed with different standards, but for this example, we're going to go with the 8x8. And then we go through a discrete cosine transform. I know that you all would have done stuff with the Fourier transform and the Laplace transform. Is the cosine transform something you all are familiar with, just at least in name? Or is this something new to you all?
I didn't specifically mention it in this course, so unless they met it somewhere else, I don't
I
think
didn't mention it
what
to
are they?
them either, so it is new.
Yeah.
Cool. I'm so glad that they waited for you to say that it was new to them before they had the confidence to be like, no, 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 we didn't know that either. Cool. Yeah, so it didn't happen in Signals and it didn't happen in DSP, which means new to you all. It is just like all the other things. It is a transform. The math behind it, we don't care right now. It is a transform which converts the image into something with a lot less energy. Now, again, that was our first stage in our compression scheme, our energy compaction. Then our next stage, our quantization. The discrete cosine transform will have a series of coefficients, which we're going to round off. And then we have a few stages of symbol compaction where we have our run length encoding and then a different type, either a Huffman or arithmetic encoding. I can never remember what this is to do with the DC component of the things, but it's not important. We have our three stages: energy compaction, quantization, symbol compaction. So I just got my eyes tested the other day, so I'm very familiar with this process. We are going to play this wonderful game of A or B. So I have image A and image B. I would like to hear from you all. Which is better, A or B? Which one is clearer, A or B? Type in chat now. All right, a series of A's. And yeah, we notice it in our sky. We have our blockiness there, whereas in A, it's not. We can see it in the sign here that it's clear that it says something in Swedish, which I cannot pronounce. And this is not even readable, much less pronounceable. But A is 2 megabytes and B is 33 kilobytes. So, time to break out the napkins and start scribbling. How much smaller is this between A and B? So our uncompressed frame is 2 megabytes and our compressed frame is 33 kilobytes. So how much smaller is it? So we have 2 MB divided by 33 kilobytes. 2 megabytes is how many kilobytes? Approximately. We could go with the approximation. All right. I saw 2000. Yep. And divided by 33. As you all have known because you had me before, I don't actually have a calculator, so this is equal to something, right? That's equal to the answer. 60-ish. All right. So let's see. I think I had it on like the next slide. Yeah. So megabyte is actually 1024 kilobytes. So oh, this ends up being over 60 times smaller. So 60 times the savings for that difference in quality. Now, we have 30 frames per second. This is for one frame. So obviously this will build up and build up and build up because we're saving 60 times each frame. So the savings grow because we have a lot of images to compress in a video. Because like think of a 5 second video that is and it's 30 frames per second. That is 150 frames. We're compressing all 150. We're going from uncompressed of 300 megabytes to whatever 33 kilobytes times 150 is. That's 60 times smaller grows. So that's why we do this. Now, that's just compressing every frame using image compression. Videos have an extra property. What is the difference between an image and a video? And I'm going to pick on my 3020 student, Brandon. What property of videos is not? What's the thing in videos which isn't in images?
Oh, hi, sir. Well, a video, the image could basically, for example, you could call it like a single frame, whereas
Mm-hmm.
a video is made up of multiple of the single frame.
And in your 3020, you were looking at two types of upscaling. What were the two types?
Oh, it's spatial and temporal.
And do you have temporal information in still images?
No.
Very good. Thank you. So, as Brandon just rightfully pointed out, images are single images, and videos are a series of images, which means we have one extra dimension, time, temporal. So, we're going to play this game again. I have one frame, the next frame, 2 frames here. Are we seeing much of a difference between these two? Yes or no? No? Yes? Slight? Uh, yeah. Okay. So I'm going to help us out and I'm going to put my laser pointer on the steeple here. It's a tiny, 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 tiny change. And that's true for a lot of video. In most videos, the changes between frames is very small. So instead of compressing every frame, we can use the difference between the frames and use that data instead. Similar is like this video right now that being transmitted to you, the compression is taking advantage of the fact that my slides are the same from frame to frame. Majority of the background behind me is the same from frame to frame. It's just my animated self, which is giving the codec a little bit of headache. So this here, and this is hard to see. This here is the difference between the two frames. So every black pixel here is represented by 0, and every white pixel here is represented by the number 255, which is 2 to the power of 8 in an 8-bit coding scheme. Do we see a lot of white pixels in here? I see like the windows kind of. I see like one side of the steeple. Compressing this is going to be a lot easier than compressing this because we have a bunch of common um, pixels. So here we go. We have the stages. This is a standard test sequence called SUSY. And what we see here is the result of a discrete cosine transform that our source image is on top. And frame 1, 2, 3, 4, frames n plus 1, n plus 2, n plus 3. And what the resultant image of a discrete cosine transform is below. what do we notice in our discrete cosine transform? That majority of the image becomes gray. That it's kind of like halves the information, but all the information is still there. That if you perform a inverse discrete cosine transform, you should still get this. Now there is one stage is missing, which was the convert to color, different color space, but we're not going to talk about that for now. Now, if we were to take the difference between images, we have our first image, and then we have the difference between image 1 and image 2, the difference between image 2 and image 3, and the difference between image 3 and image 4. And from there, we will have some motion vectors. We only need to compress one of these using the discrete cosine transform, and then the rest, we're just going to be compressing the motion vectors. And majority of the motion in these images is either really small or 0. And we end up getting away with having frames predicted based on what was there before. These predictions lead to even smaller frames. And the way which these predictions are called, we have our iframes. These are different to what I know if some of you play fighting video games, you would have heard or platformer video games, iframes as a term being used there. That's a different type of iframe. These iframes are called intraframes, which are the frames which we will compress using the JPEG compression, which we spoke about. And then every frame after that, we have our predicted frames, which is P, P, P here. And we're using not the frame itself to compress, but the motion vectors and the previous frame to figure that out. The other set of compression which we do is bidirectional, and that's what that B stands for. In this case, we have our iframe. We skip a few frames. We have our P frame, which is predicted based on our iframe. And in between, we have predictions which are based on a combination of our I and P frame. And these give us even smaller predictions. So what ends up happening is you have this group of pictures where you have an iframe, and then a couple frames after, you have a P frame, and we have our bidirectional frames, which are predicted on both our I and P frames. And this allows us to compress smaller. One of the things which is done is every so often we would need a new iframe because we want to minimize error. If we are all predicting off of something which was wrong, that wrong prediction will continue to happen. Whereas our iframes are generally the same. They're going to be as true as can be in our compression, and we move from there. So I have 2 more videos, and we're going to look at a video, the video which the frames were coming from. And this here is roughly 14 megabytes, and this is using iframes only. So let's look at it. A nice aerial shot of Stockholm. So this is iframes only, and this is 14 kilobits per second. So this is not like the entire frame, which means this 10-second clip is actually 140 megabytes. Whereas if I use the prediction frames, I have 2.5 megabytes per second, which means I'm only at 25. And I know, again, this is a transmission within a transmission embedded in Google Slides and whatnot. But to me, these 2 video sequences look pretty much identical. So we have our savings using our predicted frames to work like that. So just to remind you all, we have our basic DSP elements of media compression. We have our energy compression. In this case, was our DCT. We have our quantizer. We have entropy encoding. And then we have our compressed media here. And on the opposite end, we have our entropy decoding, which is the inverse of our symbol compaction. So our entropy coding, you will also see it as symbol compaction. I have here an inverse quantizer just to kind of match the two, but realistically, it is near impossible to dequantize signals. So a lot of images would leave this out. So we have, and then our reconstruction, which will be our inverse energy compression. And you see that we have our source I, and then we have our viewable media I hat. It will always be an approximation of our viewable media if it has a quantizer or has some loss. But usually, if there's no quantization, it is a lossless form of media, which will have a less compression, but all the information is still retrievable. And you want I to be as close to I hat as sorry, you want I hat to be as close to I as possible. You want that approximation to be as close to the true, but we take advantage in video of humans' perceptual system just not being that great and it not mattering that much. So this is important to note. Now, this is what the HEVC, the H2, one of the most common video encoders, actually looks like. I showed you the general thing. This is it with all the steps in it. You do not need to know this. And the thing which is important is you kind of have different sections within it that your encoder actually has a decoder built into it. And this is weird because you are just trying to encode that you're trying to get our input frame and get serial data. But we have all this stuff in green, creating predicted frames and then creating a prediction error. It has an encoder and a decoder in one because what's happening is as it's encoding, it's learning what the error is, and from that error, impacting how you compress everything else. This is a lot, but you will see that within this, you do have the same steps that you have our transform, you have our quantizer, and you have your entropy encode. Those are the three steps going from a source to a compressed signal. And the opposite would be, if you wanted to decode, going the opposite for it. So, lossless versus lossly, like I said, prices on the can, what they're named is what they are. You would have a lot of times where you would have lossless compression tends to get you about 3-to-1 compaction, just getting you a third of it. Whereas lossy compression, especially in like physical media like DVDs and Blu-ray, gets you a 45-to-1 or 100-to-1 ratio. Video streaming tends to try and get even more. That YouTube on standard definition will get you 320-to-1, but still very viewable compared to the raw image itself. In terms of what is used in the media industry, this is a little bit out of date because this is a very old slide, which I've been using. But in terms of the terminology that they use, they like to treat things like a house. That our bottom floor is our distribution, which is what is sent out to the consumers. This is usually in some form of lossy format. And H.264 was the market leader for a while. You would see that with the rise of open source contents, you'll see things like in VP9 or AV1 format. Usually these things don't matter to the average consumer because it is just all your devices should be able to play the thing. We're kind of beyond the era of QuickTime videos having to be only viewable on Apple devices and whatnot. The mezzanine floor is at ingest. This is when you are taking files in at the servers of media houses. And these would be some lossy formats, but minimal lossy and still large things. Because distribution will be to millions of people, ingest is just to that one server. And top floor would be lossless compression. A lot of places would just go ahead and use raw, where you have all the information without compression when you're at your media houses, when you're filming. This is a typo which I forgot to change. This should be hundreds of megabytes per second. That this is what film is essentially. So I know that you will have done transforms before, but the entropy encoding is something which I don't think we've encountered because this is a bit of a statistics thing. And this is going to be the last topic which we do. So we have a few steps which we do. So when we saw the DCT, we noticed something, that we saw all the information in the top left and everything else kind of got grayer and grayer as it went. So after a discrete cosine transform, a lot of codecs would create this zigzag pattern to get things which match each other next to each other. And you can see it if I go all the way back here. That's the same, lost my mouse. The same, there we go, zigzag pattern will be used here. That as we zigzag, we're getting to the point where information decreases more and more until we get to just that completely gray area. Cool. So MPEG-2, which was one of the earlier video codecs, only allowed predictions from the left go forward. And what you're doing here is you're trying to figure out what is the appropriate coefficients to use, and as the coefficients increase, this is like in your fast Fourier transform, you had your harmonics. In the discrete cosine transform, you'd have different levels of that. And you're trying to reduce this in such a way that if it's that you have things which are next to each other be the same. And then based on that, you should have some form of run length encoding or some symbol encoding, which we could use. So we're not going to talk about skipped macro blocks. That's completely different to what we needed to talk about, but we're going to focus on context adaptive binary arithmetic encoding and then another other arithmetic encoding. So what we're trying to do is trying to not send everything, but send some form of like cipher for our symbol, our signal, which can be easily decoded while minimizing how much we set. So we have some history here and how context adaptive binary arithmetic encoding has been used by the more modern video codecs. And Huffman encoding is what used to happen, but what happens here is it uses a bit of probability to figure it out. Huffman is not what is used anymore. This was the foundation, but what is used now is arithmetic. So as a class, because it can't be one of my sessions if it's not interactive, we are going to use this and try and figure out how this works. So in this example, we have the following symbols: A, E, I, O, U, and exclamation point. What each of these symbols has a probability of occurring in whatever signal this is. The probability of an A occurring is 20%. The probability of an E occurring is 30%. Probability of a I occurring is 0.1%. The probability of O occurring is 0.2, U 0.1, and then exclamation is 0.1. So it means we could assign some ranges from 0 to 1 for each of these things, kind of drawn like this ladder. So A goes from 0 to 0.2. E goes from 0.2 to 0.5. I goes from 0.5 to 0.6. O goes from 0.6 to 0.8. U goes from 0.8 to 0.9. And exclamation goes from 0.9 onwards. So in this example, we are trying to encode an E, an A, an I, an and an exclamation point. So the way in which we do this is we assign ourselves a range. And to get our E, we know that it must be between 0.2. Our symbol which we're sending is between 0.2 and 0.5. All right. So that's our first symbol. We know that the value which we're going to send needs to be between that. Then we have this range here. It's not very easy for me to draw it here, but this range here goes from the lowest value is 0.2 and the highest value is 0.5. And our intermediate steps would be in between there. So if we're going from 0.2, I'm going to just reuse the first diagram now. That's not what I want. I'm now going from 0.2 to 0.5. And I need to divvy up this in such a way that it matches the probabilities. So how would we do this? We would look to see, okay, I have a range of 0.3 in between, and the probability of a number in between these things. So we're starting from, instead of going from 0 to 0.2, we are starting from 0.2 and going to 0.3 times 0.2. And that is 0.26. And then the next set, that did not work as well. From 0.2 to 0.5, no, we want the range that we're going from 0.26 to 0.3 times 0.3 plus the 0.26. And that should be 0.35. And then we repeat this process going up. And after that, our next calculation would be going from 0.35 to 0.3 times 0.1 plus 0.35. So that should be 0.38. And we continue all the way up. So we're going to just finish this off just to get our range. I'm going to not do the rest because they're not relevant for us here. What is our next symbol here? A. So it means that our values need to be between 0.2 and 0.26. So you see how we're going smaller and smaller until we get each of these. So the E indicates that we have to be between between 0.2 to 0.5. Then the next symbol, A, means that we have to be between 0.2 to 0.26. And what's our next symbol? It's an I. We repeat this process until we get all of our symbols done. So I'm going to leave you all to try and get me the ladder for I in between 0.2 and 0.26. I'm going to erase everything now and kind of neaten this up so we could kind of get an example, figure it out. So we're going from 0.2 to 0.26, and we want to draw this ladder out to figure out what's here, because that's what like this one is. So just to get us a bit of a habit, what we need to find out is what is the range. And then from that, we figure out what is our start to our end. And our start usually go to our end, and our end is actually our start plus our range by probability. So your task in the next 3 minutes is to tell me what the range of I should be in this. But if you have any questions, feel free to ask in the chat or unmute and ask. I'm going to drink some water. Okay, so I've done the first couple steps that we're going from 0.2 to 0.212 for our range of A. And for E, we're going from 0.212 to 0.23 for our range of E. And I'm letting you all tell me what is our upper bound here using that same thing. Let's check the chat to see if I have an answer. Akshay, Adrian, 0.236. Cool. I'm happy with that. And then, so that is, we've done this, we've done this, we've done this, we need to do this. So trying to get there, need to go from what will be our new bottom of our range, 0.236, and what will be our top of our range. Sorry, wrong way. That was 0.23 to 0.236. Good. And then we're going to have to do the same thing and then repeat it for this. And then we should get one value to represent these 5 symbols. So it should be like 0.236, sorry, 23 something, something, something. And this one value should be easier to send than these 5. The other thing to note, the more common the value, the more common the symbol, the smaller the value should be. The higher probability symbols should be a smaller arithmetic number.
Oh, so Daniel,
Yeah,
just to be clear, after you encode those 1, 2, 3, 4, 5 symbols, by the time you reach the exclamation point, you'll be down to one
one
number
arithmetic value.
sequence, one value.
Correct.
Okay.
And that's how this would work.
So it keeps getting smaller and smaller until you just get one, and then that's what you send.
Yeah. Or more and more, not smaller and smaller, but like more and more precise, more decimal
Yes,
points.
right. Okay.
Yeah. Going to clear this off again, and we have the time. We'll finish the working this one out. So we're going from 0.23 to 0.236. So 0.23 to 0.236. And we are trying to get I again. So let's see if we could get that. We can find each one of these, but let's cheat a little. We know that this base would be 0.5, so 0.23 plus 0.5 times 0.06. And it's 0.233, 0.2. So we now have a value between 0.233 to 0.239. And then our last round of this is here. And this is going from 0.233 to 0.239, which means our bottom value should be 0.233 plus 0.9 times 0.006. Two, 3, 8, 4, and then 0.238 plus 0.1 times 0.006. Oh, we already have it, 0.239. So if you send any value between 0.2384 to 0.239, someone who has this probability table should be able to decode it to know that the symbol sent should be E-A-I-I exclamation point. And that's how this works. Any questions before I move on to wrap this up? We could always come back if there are questions. So, right. So in summary, video is super common on the internet. How we compress video takes advantage of the fact that it's a series of images with movement. Video compression is applicable to film studios, media streaming sites, and user-generated content. And the user-generated content such as social media companies. And that's pretty much it. The main thing which I would like you all to remember is the general structure of compression and Yeah. If we have any questions, go ahead and shout them out. Otherwise, I'm going to run away to CSL. And yep, let's see Fazil unmute.
No questions?
And well, y'all know where to find me. I'm in this office or wherever. I'm not an ocean away, unlike Dr. Ali. So if you have any questions on this after the fact, you can come and ask. If you want to find out a bit more about my experience at Trinity and the video work done there, I will gladly talk about those another time if on one-on-ones and whatnot. But other than that, I would say good luck with the rest of the semester. And yeah,
Okay, and we will after the 30-20 week next week, we'll schedule some review sessions. They will be online and so on. Now, by now you have access to all of the problem sets and all of the past papers. So it's really now in your court and like Daniel said, I'm available. You just have to message me and let me know what's happening. Okay? Okay, let me stop the recording.